the presentation, got an hour or so? Okay, so we'll go over kind of what Lam Research does, the industry that we're in, and I'll spend a bunch of time at the end. We can talk about opportunities for college graduates for internships as well. My name is Shirley Johnson. I'm actually from our college recruiting, so if you want to find out any of the full details, she's the one to ask. So I get to understand where you guys are at. Everybody, college of chemistry? Either chemie, how many chemie? Okay, chemistry, the rest of us? No, what else we got? Oh, combined. Okay. Good, okay, my background. So I've been in kind of the semiconductor equipment business scarily for 24 years. Started as a new college graduate, went to Applied Materials, spent 5 years there, went to a startup 5 years, public, licensed our technology to Lam. We've been here for 15 now. My background, chemical engineer, did undergrad at Wisconsin, actually took transport from Berkeley to Stewart. So we got the BS, they still use the BSL, Berkeley Stewart Lakeford. I think it was always the classic, practically dead when I took it so long. And then came out here, went to grad school, got a PhD in a small private school on the peninsula that has a decent football team. Stanford. But right now, I'm actually on the College of Chemistry Industrial Advisory Board. So get to meet once or twice a year with Matthew and kind of sit down and really see what's going on. So this is you'll see some of the statistics we've got. Cal is by far our biggest recruiting place, especially for high-tech engineering talent. And what I want to do today is, well, first of all, before this thing had kind of gotten published, how many of you have heard of Lam Research? Okay. So we don't do animal testing. Okay, that's the first thing. There's no B on the end of Lam. Okay, it was actually David Lam who started the company about 30 years ago. Some people are like, hey, I like to get into animal research. It's like, no, that's not us. Okay, so what I'm going to do, I'll talk about the industry a little bit. I'll talk about our products and technology. And then I want to give you, you're just getting out of school. Oh, actually, how many seniors? Anybody else? Yeah, she's doing it early. It's good. Because the future is really what, if you get into this industry, this is what you're going to be seeing going forward. And then we'll spend some time on the college programs. So, how do I explain to my parents what Lam Research does? Besides, we don't do testing on animals. So you take any piece of electronics. So it doesn't matter what it is. It could be a laptop, tablet, iPhone 5, this Surface coming out this week, and you open it up, which you shouldn't do unless you want to really screw things up, and you'll see printed circuit board. Pretty obvious. Everybody's seen these. And on the printed circuit board are a bunch of integrated circuits, a bunch of computer chips. Take one of those computer chips, and I open it up, and what do I see? I see a pretty complicated integrated circuit. And it's got graphics processor units. This is an ARM processor, probably the A5 from Apple. There'll be NAND flash, there'll be memory. Any chip will look like that. Get a scanning electron microscope, go down a little further, and what you'll see at the heart is some very small structures. So transistors, interconnect wiring. So that's really what's making these devices tick. But how do you make these? Well, that's what Lam Research does. We make the equipment that process the wafers, that make the chips that go into every single piece of electronic equipment. And in fact, I can safely say that if you buy any piece of electronics today, maybe a car, anything that has a chip in it, that chip will have gone through a piece of Lam equipment. There is no chip made today on any sort of leading edge application. Every USB stick, because we are in every chip maker in the world. And so I like to think it kind of as the engine that helps keep the nanotechnology moving. So we make equipment that's used for some of the processes. Every chip, but not every single process. And we'll talk about the steps that it takes to make a computer chip. But before we do that, let me tell you a little bit about the culture at Lam. We have a mission statement, we have a vision statement, and core values. So, and a lot of these, you'll see most companies have these, and they're either hung up in the cafeteria or something. But we spend a lot of time thinking about this, and we try to write the words on there, and actually make sure we stick to them. So, we are world-class, we try to be world-class. We recognize, I'll talk about our customers in just a minute, but you can kind of guess, you got Intel, you got places, where do they make the chips? And we really focus on innovative technology and productivity, because these are things, they have to make money when they make these chips. And we're focused on the semiconductor industry. So we're not doing bio, we're not doing solar, we're focused on leading edge chips. And what do we see, when do we know we're being successful? Well, our customers will kind of say, we like working with Lam. You just ask them randomly anytime, that's what we want them to say. We're the #1 company in whatever space we occupy. And I'll go through kind of all the pieces of equipment that we make. We recognize in order to do that, we got to have really good people. And successful people want to work at successful places. You don't want to go to some place where you're just kind of this cog or whatever, or a place where you're #2. So that's why we say we want to be #1. And that leads to kind of the best products and services and financial performance, so that we can pay the people that we hire and also fund the R&D and actually have a decently traded public stock. In order to do that, so this company where successful people want to work, these core values really come into play. And again, this is more than just a poster sitting on a conference room wall. These are things that we actually kind of reward, we emphasize, and you look at it and you kind of go, okay, most of these are fine. But it really, if you have a company that is doing all these things, most of the stuff over here just kind of happens. So achievement, honesty, integrity, open communication, you'll see these. And we'll talk about those. When we recruit, these are actually on our internal recruiting forms. We not only look at, okay, how's the resume look? How do they do in all their classes? Whatever on test scores. We also look, will they fit into the culture? And this is kind of, when we say culture, that's a good way to kind of summarize it. So we're a global company. In fact, I didn't even put down, we did $4.2 billion in sales last year. I think I've got another slide. We got about 6,600 employees worldwide. And we are everywhere we need to be. 80% of what we make, those pieces of equipment I'll describe for you, go to Asia, because most of the chips now are being manufactured in Asia. So Korea, Taiwan, Japan is some, although it's kind of dropping down. And we really focus on kind of leading edge. You'll see we've got other sites where there are existing kind of legacy fabrication factories, we call them fabs, wafer fabs. But really, most of the leading edge work is here, and then you've got Intel in the U.S. and a couple of IBM in the U.S. and Micron. We'll talk more about the customers. Okay, so I mentioned on one of the slides I used the phrase wafer fabrication equipment. So I want to show you kind of how that fits into the ecosystem. And what is this? We got these pieces of equipment that process these semiconductor wafers. And like I said, we'll spend plenty of time talking about what's going on in these systems and how engineers help decide and design what's going on there. But that market worldwide for all the companies that make this type of equipment is about $30 billion a year. And on top of that, there's another 30, so kind of 60 total capital when Intel builds a wafer fab, when they build a factory to make chips. And they and all their competitors make enough chips to total up to about $300 billion in sales a year. Okay, so this is the spot where you get an Intel Core i7, or you get a 64 gig NAND flash out of Toshiba or SanDisk or wherever, and then that feeds a $1.6 trillion global electronics market. So again, it's just, we take it for granted nowadays. You got a solid state video camera at the back of the room. Everybody's probably got a flash drive somewhere on their keychain chain, or your car takes a ton of chips now, semiconductor content, and then let alone kind of military communication. It's everywhere. It's more than just iPhones. So it's a semiconductor, and because maybe most of you probably haven't taken a wafer processing class, real simple kind of, let's just get a baseline. So semiconductor is kind of a partial conductor. It conducts some of the time, once in a while. You can dope it in a way to make it a conductor, or there's a form where it's a resistor. So if you think about it, if I have a conductor and an insulator, essentially, it's a wire, right? I got copper in the middle, and I put some plastic insulation around it, I got a wire. And with that wire, I can do all kinds of stuff. I can turn switches on and off, I can move signals around, I can store bits of information. And that's really all that happens, but on a very, very small level. And so, if you look at what is processed in these pieces of equipment I'm going to talk about are wafers. So they're pure silicon, single crystal silicon wafers that are actually pulled out of the correct diameter. Right now, everything's 300 millimeters in diameter, so it's 12 inches across, essentially. And when they make the wafers, they have molten silicon, and they basically pull them out in these long tubes of solid single crystal silicon. It's a very slow process, and you basically have you put a starter crystal in, and then all the silicon, as it gets pulled out and cools, will arrange itself in a lowest energy state, and that turns out to be single crystal. And then they take these things and slice them into little discs, and polish them and everything else, and then that's your starting material to build up an integrated circuit. So you take that blank wafer and you start running it through these pieces of equipment. You deposit layers, you put masks down to remove selectively different portions of the layer. I got some conductors, I got some dielectrics, there's some resistors or insulators, and eventually I end up with a pattern that with multiple layers on it. I'll show you some cross sections of those. At the very heart, there's a small transistor, and that's really all that these things are. They're just things that can turn on and off. And how you do that and how you wire them up can make a memory device, it can make a microprocessor. And on this wafer then are hundreds, can be even thousands if you're doing some memory applications, of individual die, individual chips, that when they're done being processed, they'll get sliced and then packaged and then stuck on a circuit board in a computer or on a phone. Okay, so, and just, you have to have how big's a human hair and all these things. So we're working at 36 nanometer. I mean, it's continually just shrinking. I'll show you actually kind of Moore's Law, if you've heard of that. These things get smaller and smaller every generation, and so a human hair is 17 microns, so that's 17,000 nanometers. You can see we're a lot smaller. At some point, we need something else to compare it to. But, so customers, we talked a little bit about it. It's worldwide. You can see pretty much anywhere they're doing high tech is a wafer fab, and if there's a wafer fab, there's Lam equipment there. The big three are Samsung, Intel, and TSMC. Now, that's kind of by sales, kind of by the amount of equipment they buy, but the real measure in my mind, because I'm worrying about research and development, is these are the customers that are driving the technology roadmap. They're constantly saying, look, I need to shrink, I need to do this faster, I need to do it smaller. And so it's IBM clearly has a great R&D group and they help, but they're just not as big a player anymore. And so you can see it is truly kind of a global business. And please stop me, you get questions, it's fine. So here's the revenue. I mentioned 4.2 billion calendar year 2011, and over the last 3 years, kind of if you add these together, 1.5 billion in R&D for Lam research specifically. Okay, and there's a bunch of detail on the slide. I mean, here you can kind of see Southeast Asia, China, Taiwan, where we sell in a particular year. You can see kind of Taiwan suddenly is a big portion of it. Intel didn't buy here, and then they buy more. Europe kind of hanging in there at the bottom. Japan, not as much of a factor as they used to be. The big thing on here, from my perspective, is it's a very cyclical industry. So they build it, so they, okay, let's pretend you're a memory maker. You're either Toshiba or Micron or Samsung or Hynix. And you make NAND flash. And Apple comes by and says, we're going to be making the iPhone 7. And it's going to have 50 gigabytes of DRAM and a terabyte of flash in it, right? And you're like, this is great, you know. And they're like, oh my goodness, we'd never be able to fill those orders. And so they start building these factories and they start buying equipment from us, and it's great. But the problem is, it's a competitive industry, and not everybody kind of plans for, okay, I got to have this much capacity. But then when they get to the end, Apple's only going to buy one set of those chips, just as much as they need. So you end up with a big boom for us. We're selling equipment like crazy, and they go, oh, we got enough. We got, in fact, too much. And then the prices of NAND, you know, I always benchmark fries. And I can kind of tell, oh yeah, that was when we sold them all this, and then suddenly the prices drop at fries because there's all this extra capacity, all these extra chips flowing out. So this was a little bit weird because remember this was the Asian, or the big banking crisis here in the US. So there was a macro factor on this. But the main thing from my point is, we see this huge, I mean this is a factor, you know, it's cut in half. Our revenue, you know, $4 billion down to $2 billion. Our R&D hardly flinched. In fact, most of this was just kind of, we took away, we have bonuses and profit sharing. When that drops away, okay, that took away this. We kept spending. In fact, a lot of times the strategy is you spend in the downturn, so when they come back, you're ready to grab more market share with your new products. And so it's a research-intensive industry. In fact, if you compare it to even like an HP or more of these kind of end-user, even Cisco, and just ratio, take 500 million divided by 4, that 20% of our revenue is going back into R&D a year. And so that's a big, big number, at least, I mean, that's even in the low times, right? So that's a R&D intensive industry. That's why we need so many engineers and scientists. All right, we're going to talk about products. So if I take one of those chips, here's that transistor we looked at before. On this, so I grab an integrated circuit out of a laptop and I section it, put it in a scanning electron microscope. I get a picture that looks like this. At the very bottom, this little square is actually the transistor. So even on this scale, where we're blowing up millions of times, it's a small thing. Okay, and all the rest of this up here is just wiring to connect the billion transistors that sit down at this level. Okay, because remember, a leading edge microprocessor will have a billion, or a NAND flash will have a billion gates at the bottom. So this is the thing turning on and off, and this is all the wiring. So this light part is copper wire, and then the dark part is kind of the insulator, the dielectric material around it to keep the signals from interfering with each other. And then up here, this is the thing to kind of get the signals all the way out to the package, the pins on the actual integrated circuit. Okay, so if you're deciding, okay, I'm going to be a chip maker, I got a great idea on how to make a chip, you're going to have to buy a lot of equipment. That's why it's a $30 billion industry last year. And there's a bunch of steps, and it's too complicated to go into everything here, but you do these things many times. They're not all sequential like this. You may do the wedge and depth and clean. And basically what Lam does is these core in the middle here. So we do etching of materials, kind of removing them off the surface. We do strip, or a photoresist removal step, and I'll show you more about each of these. Cleaning up the mess on the wafer after every step, and then depositing films that end up being etched later. So I'm going to go through. The reason I put this up is so here are those 4 areas: etch, depth, strip, and clean. And then we also have a good business you can imagine. A system that I showed earlier is you can figure $5 million a piece. So these are not cheap things. So if you're an Intel or a customer that's making chips, you want the thing to work. If you're spending $5 million and you want it, it's just like a car. You got to go in and do preventive maintenance. You got to change the oil. And so we have a big division that does all of that as well. But within the kind of the core products, what I wanted to show is that it's not as simple as just, it's an etcher. I mean, they're all etchers, but we got a lot of different types depending on type of material. Same thing with deposition. And we'll talk about some of these different types of, this is depositing dielectric, this is depositing a metal, and they all have a different function. So where are we sitting kind of in the industry? Because remember back that mission statement and the vision was we're going to be #1 in everything. So we're not there yet. That's otherwise I guess we need to take a vacation or something. But we are #1 in etch. We're #1 in 2 of the deposition steps. So this is electrochemical deposition. Many electrochemists will like this. This is tungsten chemical vapor deposition. So another deposition of a metal where we're #1. And then plasma enhanced chemical vapor deposition and high density plasma chemical vapor deposition. We're #2. We're working on being #1. In removal of that photoresist, #1. And in single wafer clean, #2. Working on #1. And I'll walk through most of these just to kind of give you a cartoon on what this stuff looks like. Now, one thing that popped up that I haven't mentioned is what's this Novellus thing sitting around. So Lam so Novellus Systems was a company that did deposition, and Lam got its start doing etch. About 5+ years ago, we bought an Austrian company that made wafer cleaning equipment, because the step typically after etch is clean. So we're like, okay, put those together. It's like a Reese's peanut butter cup. It should be good. And so we were kind of good there, but they just said we don't have any of the depositions, so we merged with Novellus this last year, kind of finished in June, and became a much bigger company. And now we have a broader array of products as well. So that's the Novellus, and they're no longer Novellus; it's all Lam Research. So if I take kind of these steps and look at it in a very simple cartoon, I got a wafer coming in. So this is that circular piece of silicon. And I have to put down some sort of layer to be patterned later. So this could be silicon dioxide, this could be silicon nitride, it could be copper, it could be any number of films that you need to build up an integrated circuit. But in order to pattern it, I want to end up with something that looks like this, where I've got maybe some lines, those transistor-like structures. So again, I'm looking at the cross-section here. How do I do that? Well, I have to put down use actually a photographic process, although it's on a very, very small wavelength scale, where you put down you spin on this green layer would be spun on as just a polymer essentially, but it's an optically sensitive polymer. And then I have a mask of what I want the pattern to look like on the wafer. I shine a light through of the right wavelength. In this case, it's a UV exposure, or a UV light source. It's blocked where the mask is opaque, and it transmits through. And where it transmits through, it'll cross-link. So I end up with a region where, when this polymer layer is on there, this is hard, this is soft, hard, soft. And basically then I can chemically remove, I can wash away the soft parts. And I end up with this layer that's the pattern that I want, but it's in polymer. That's a material that's not going to last on a silicon wafer. So we use that in an etch process to transfer that pattern down into the underlayer. So whether it's silicon dioxide or silicon nitride or a metal. And then, so that's the etch part. And then I need to remove that mask. And so that's the strip where photoresist removal. So I'm removing this photosensitive, and it's called a resist because it's photoresist because it's photosensitive, and it's nominally supposed to resist the etching process. It's got to stick around long enough so we can finish kind of clearing out the places where we don't want the material. And then, as nicely indicated by our little red dots, there's going to be some residues, because remember, this material's getting removed, and some of it may stick around, so you need to do it clean, because you can imagine on these small scales, if I have any sort of impurity on there, it can easily trash the transistor. Okay, so here are the Lam processes. So I'll walk through each one of them. And we'll kind of look at it in a cartoon way, what are different ways to do it. So I'm going to show you 3 different types of deposition, and there's kind of a hybrid in the middle of one of these. So one is physical vapor deposition. So I bring in, so I've got a vacuum chamber, and I bring in what we call a target, and it's just a piece of the metal that I want to transfer to the wafer. So it could be made of copper, could be made of tantalum, could be an alloy of like tantalum and carbon. And then I put the wafer down here. And so remember, I'm in a vacuum chamber. And I put a plasma. And you see plasma is here all over the place. So we'll actually hire a lot of plasma physicists as well. So if I flow argon in here and I turn on radio frequency power, I basically can get this induced field coming from this metallic plate to rip off electrons off of neutral argon. So I got just argon gas floating around there. And electrons are easy to come off if you have enough power. So now I've got an ionized gas. So I've got electron soup and Ar plus ions sitting in there. And I can now use that to accelerate those argon ions, which are relatively heavy. They're in the gas, and I can accelerate them so they bombard this target. They sputter off an atom, and it's going to go line of sight because it's low pressure down to the wafer. And so I'm basically transferring a layer of metal from this target that I used onto the wafer. And we should look like this. Okay, so that's our physical vapor deposition. So it's just a physical process, right? I'm just sputtering, I'm taking these, I'm bombarding this target with little projectiles of ionized argon. And okay, here's copper, titanium, tantalum. So now there's a variation on that where instead of physically doing something, I'm going to take that same vacuum chamber and this time I'll put in a shower head. So again, it's made out of metal, but this is not going to be participating, hopefully, in the reaction that's going on. Put the wafer down below, and I need to flow gas, so reactive gas. So this is chemical vapor deposition. So if I put gas, I want to put it uniformly across the top of the wafer. So now I've got these two red and blue gases coming into the wafer, and I need to give it some sort of energy. So if I do just chemical vapor deposition, these gases will condense on the wafer. I give it heat and it reacts. So you kind of got blue plus red equals, what do we have? Purple. Not here. And so there's two different ways to do it. One is I can have the gases, again, condense, turn on some heat, and have it react. And pretty straightforward, right? Just a chemical reaction. An example of that is if I take silane and ammonia, I can make silicon nitride, which is a good insulator with unique properties that you want in the semiconductor device. I can also put some RF power on. Same thing that we did in PVD. Remember, it was the RF power was up here. And RF just means radio frequency, so it's going up and down. And it's causing this oscillating wave, which will, again, rip off electrons off of the supply gas. Those gases can actually then react in the gas phase and kind of deposit on the wafer. So that's plasma, that's the PE part, the plasma enhanced. So I can have just a chemical reaction where I'm having it done and it's thermally driven, or I can add in a plasma component and make it much, you can imagine, much more reactive. And so if these ions come down, a blue and a red ion come down, they're going to very quickly react. They're going to want to recombine if they've been ionized as well. So that's a good way to put down insulators. Okay, electroplating, classic chemistry problem. The Nernst equation is somewhere. So I take a bath, sulfuric acid, copper sulfate, and I put in, again, now here's my source of copper. So analogous to kind of the PVD, except it's now immersed in this bath. I put the wafer on upside down in this diagram. So it's all in this bath. And you notice there's actually a copper seed layer on here. This reaction won't work unless this is a conductive surface. So we use that PVD process I showed you before to put down that first layer of copper, and we take it, put it in this electroplating bath, and you hook up your Duracell battery, and you'll just get a standard electrochemical reaction right here. And what happens is the copper will then migrate from the cathode to the anode, and I plate the copper. But it can be in very small features. So I can have spaces on those transistors. I can be coating it if I wanted to with copper. And it's a very precise way to grow a lot more copper than just kind of a single layer. I want to jump back. Go back to here. I want to give you one other variation on this because you may run into this. And I talked about the chemical vapor deposition. So I'm flowing red and blue, no plasma. They're both sitting on the surface. I heat it, it reacts. Okay. There's a method, actually Finland was the first place they did this about 20 years ago, called atomic layer deposition. And that takes advantage of special precursors. And in this case, You have a special red, you flow that only by itself for one step. And it's chosen so that it'll make an atomic, it's self-limiting. It will only coat on the wafer. It won't coat on itself. So you only get one atomic layer across the surface. And then I flow blue, that'll only form one atomic layer on the surface of red. And then I do a reaction step, heat or whatever to trigger it, and it forms, in this case, purple. One layer. So it's you're literally doing one atomic layer at a time. Which you can imagine, very precise. I want to grow, an atomic layer, what's a bond length? The carbon-carbon bond length is about 2.5 angstroms. So I can make stuff on the order, of tenths of nanometers and build it up. Great for precision, terrible for throughput and efficiencies, right? It's going to take a long time. So there are certain, like the transistor in every one of the Intel chips today has an oxide layer that's the gate, the thing that helps turn the transistor on and off. It has to be super thin. And so they're putting down, and it used to be silicon dioxide, but the silicon dioxide can't take it anymore. I have to keep making it thin. Now it's so thin that it's leaky. And so they moved to a rare earth metal, hafnium. They make a hafnium oxide. The only way to put it down is with this atomic layer process. And the good thing there is they only need a few layers of it to make a good transistor. So that's another kind of chemical process that's used in this industry. Okay, so you take all that science and engineering, and you got to put it into a system that can not only make it work on a single chip, it's got to work on a big wafer, it's got to work on thousands of these wafers every day. And so there's a whole pile of engineering beyond just kind of the basic science to turn these things into production systems. And that's why it costs $5 million a pop buying one of these systems. So you can see here, this is the plasma enhanced. I didn't talk really about, there's a super plasma enhanced, a high density plasma. So you really crank it up, and that allows you to fill certain features that kind of standard PECVD doesn't work. Here's that tungsten atomic layer deposition or chemical vapor deposition. This was that electrochemical deposition we showed with the copper, and here's that PVD, the physical vapor deposition as well. And then, interestingly, some of these materials, like this one, need to be kind of cured even after you put them down. And so we have a product where it's basically just ultraviolet lamps. And you put them in different stations, you kind of see the lamps that come down right over the wafer, and you shoot the lamp on, and it does kind of the curing of that film to make it tougher. All right, let's move on to etch. So plasma etch, same thing. I got a vacuum chamber, and I put in this electrode. It looks similar to the PECVD, if you remember, and there are a lot of similarities. Except in this case, I'm going to put a power generator up here. Remember, every time you see that in a vacuum chamber, that means, oh, I can make a plasma. And I do the same thing now on the wafer. So now, remember, I've gone, let's go back real quick. I deposited in the last all those products I was telling you before. And then there's this step in between that Lam doesn't do, where we have this optical lithography, this step where I'm transferring the pattern onto a photosensitive polymer. That's done, and I take that incoming wafer, and that's what's going to go into my etcher. So here's the wafer, here's that film we just deposited, and here's the layer. So at the end of the day, we want just this pattern in the blue with no green on top. Okay, and you notice I've got another radio frequency generator. I got another power supply down here. So, same thing, I'm putting in gases, but now I don't want them to react to deposit. I want them to etch away with this blue material. Okay, the trick is, how do I tell the gases? So I'm going to make them a plasma. I'm going to, again, turn on the RF power, and I'm going to rip off electrons off of the atoms, and I'm going to have an ionized mix. So it could be chlorine and oxygen, for example. And I'll have Cl plus and an electron float around, and O plus and an electron float around. And that's all in this soup up here. And then I use the power down here to accelerate those ions down to the surface. And if you pick your gas, this is what chemists and chemical engineers do, is you have to experiment and figure out what gases do I want reactive species will etch the blue. That's actually pretty easy, but the problem is I can't etch the green. Because if I etch the green, that goes away and I don't have my mask anymore, and I'm just kind of, everything's gone. So it's not as easy as it always seems, but in PowerPoint it's great. So the blue goes away, or the purple. And in this case, if I was etching, if the this purple layer was silicon dioxide. I could put in carbon tetrafluoride and form a volatile byproduct that both CO2 and the SaF4 will get pumped away. So we've got, again, in a vacuum chamber, and those byproducts go away, and everything's great. So if I look at what are the products that we have in the etch series, so again, those chambers, that little schematic that I showed would be sitting right here. That's what this box is enclosing. And underneath is where the pumps are, and the top is where the radio frequency generators are. And we basically have to design different types of plasma technology to etch different types of materials. So this etches things that are conductive typically, so silicon, but not metallic conductive, so the semiconductor conducting materials. So primarily different forms of silicon. This will etch dielectrics, so the oxides and the nitrides that are used as insulators, and this will etch, typically it's aluminum. The copper, turns out you can't etch. You have to do it with aluminum, time to go into how you do the copper, but you basically have to do a reverse process where I etch the hole and then fill it up with copper, as opposed to putting on the copper and then etching it. And then we have others, so if you've heard of MEMS, microelectrical mechanical systems, you can do, there's a lot of silicon etching in that, so we make a version of our etcher to do that. And this TSV, through silicon via, part of the challenge people are looking at now is the chips themselves are actually, the transistors are so small, connecting a logic part, a transistor, to a memory is actually pretty far, even though on a chip scale it doesn't look very far. And so they are finding that if you stack the chips, I take an Intel microprocessor and I put a DRAM chip on top of it, as long as I can align them properly, I can end up getting a very high performance stack. And that's, you have to etch all the way through the silicon in order to make contact with that chip down below. So that's what this etcher does, through silicon etch. Okay, we're now down to the photoresist removal step. So remember, we put down the layer, we've etched the pattern onto it, but I still have this green photoresist, which I don't want on the chip in the final package. And that essentially looks like an etcher. It's just there, you'll typically run oxygen. So the photoresist will be some sort of polymer, right? CXHY, could have some oxygen in it. And you're essentially just burning it off. You're forming water and CO2. And that's a relatively simple thing. You turn on this plasma, you get ionized oxygen, it'll react to the carbon and the hydrogen, and the green goes away. Again, it's got to be selective. It better not start etching this underlayer material. So this, writing this down seems really simple, but in reality, that's why we have so many process engineers, chemists, and chemical engineers. And that gets converted into yet another set of products, strictly to remove photoresist after etch. And we have, it turns out that when you're making a logic chip, so logic chips are like graphics chips, the central processing unit in a phone or a laptop. You need to, there's a different set of requirements there because the transistors are maybe a little more fragile versus memory where like a NAND flash or a DRAM, that you just want to crank through. It's actually a pretty easy thing to do, but it's got to be really fast. So this is a little more precise and this is fast. Oh, and then we've got a version of it where you say, well, wait a minute, the step after etch and strip, why don't you just put them together? And so we actually put them on the same system. And I think you should take a step back. I didn't even explain, when we're processing these wafers, there's a box of them in the fab that comes to your tool. It's all automated, so all robotic stuff. Delivers a box of 25 wafers to like a stripper etcher, and it gets put on the front of the system in a special shelf. And then we have robots then that'll take each wafer and we'll put it into multiple chambers. So we can have multiple etch chambers. In this case, we've got an etcher and then a stripper. So we've got a robot in here that'll, okay, it's done etching here, we can remove the photoresist on the same platform. So that's another reason why these things cost so much money, because we have to have robotics. And you remember we were talking about how any contamination will kill the device. These things have to be super clean as well. So we're moving around, yeah?
How many chips can you put on a wafer?
So a logic chip, which is much bigger, you can get 100, 200, say for like an Intel high-end processor. Memory, if you're looking like at a DRAM or a NAND flash, you could have many hundreds, 800 up to 1,000. I've seen wafers with 1,000. And we talked about, I mentioned the micro-electromechanical systems. So that, one of the ones there is like an air pressure sensor for your tires. Some of the cars will say, oh, you have 32 pounds of storage or something. Those things are so small, you can get like 10,000 of them on one wafer. And because they're just these tiny little things. Yeah.
So approximately how many transistors do you make per like, silicon wafer?
Yeah, so that's actually a good point. So Intel always talks about, hey, we got 1 billion of these on our chip. I mean, we're approaching 1 trillion on the wafer, and every one of them has to be good. And that's people don't really. We have to make sure every one of those is good. And if they're not, then okay, that's why they get they talk about yield. How many of the chips are actually good? What fraction of them are good? And so if you can imagine if you're Intel, I have a couple hundred of these high-end server chips on there. At the end of the day, I mean, every wafer is tens or $100,000. And I got a box of, I'm walking around with a box like this, and that's like a good starter house somewhere in the valley here. $100,000. So we got to be very careful as we handle them. That's why our robotics have to be very precise as well. Okay, let's move on to clean. So in the cartoon, everything's not as clean as the PowerPoint kind of showed. So once you're done with the etch, I can have residues. So remember, I've got silicon combining with oxygen or something, but it may not be volatile enough, and it sticks on the sidewall. And so now I've got something that's not the blue. It's it's halfway reacted, but it didn't get pumped away. So or it may have something that in that deposition process where I had a reaction occurring in the gas phase, and it kind of rains down on there, but it's not the right species that I want. So I get a particle. Or I have somebody, there's just a dirty grease or something from the robot or something if you don't have it working right. And so basically at every step along the way, there's a chance these things won't work. The transistors will get shorted out if you have junk on them. So cleaning is an important part. It's kind of a necessary evil. And in this case, we're talking a lot about vacuum processing now. This is an atmospheric, so I'm basically taking kind of a Teflon tub, an expensive Teflon tub, putting the wafer in. I've got a drain system, and I bring in a chemistry, an arm to dispense chemistry. So it's a straight, kind of acid or a special solvent, and I start rotating the wafer. And then I start flowing the chemistry, and it's got a bunch of nozzles on it. It'll come on, and the magic chemistry, wafer spinning, the arm's moving around, and suddenly it's PowerPoint clean. And so it's pretty straightforward on the acidic side of things. I mean, it's stuff you work with, sulfuric acid, hydrochloric acid, hydrofluoric acid. And then there are some much more subtle organic solvents. And there are whole companies in the industry, Lam doesn't do this, where they just hire a whole bunch of chemists and they start making custom chemistries. Because you can imagine trying to remove certain things. Because now I'm spraying on acid, I better not be touching the transistor while I'm doing that. So you got very complicated buffer solutions. It's a big business. And you can dump it, but you can imagine a green perspective, and it's expensive. I'd much rather reclaim it. So there's a whole industry on how do I take these waste streams and recycle them into something that I can use back in on a good wafer. So Lam has, so it's spin wet clean, so it's single wafer, one wafer at a time processing, and we're always spinning the wafer in order to get uniform dispensing of the chemistry. So we've got two different versions here, kind of a high volume and a lower volume. Packaging is when the chip is kind of finely made, you got to put it into the package that goes into the circuit board, and they need some cleans there. And then there's an interesting application of plasma technology. So this is all just, again, you're taking a garden hose and spraying the chemistry on the wafer. In this case, the edge of the wafer is called the bevel. And we actually make a system, you can see the wafer sitting in here, that when you close this lid, there's a plasma only on the extreme edge where there's no circuits. But it turns out that as you're processing the wafer, through all these steps, junk will start to accumulate kind of on the edge of the wafer. Because you're cleaning all the time, very much in the middle. You're You're very conscious about these, where the chips are. And the edge doesn't really matter, except what happens in subsequent processing, you get thermal expansion or something, stuff will flake off and then pop in the middle of the wafer. So we created a whole system where it just etches away the junk at the edge of the wafer so it doesn't later pop on to the middle. Again, you never think of, well, in the world, who thought of that? Well, they started losing chips because they weren't working, and they went in and, why is this junk there? Turns out it was from the edge of their wafer, and so we came up with a system that okay, so that's kind of semiconductor processing, where Lam fits in. Let's talk about kind of where things are going. So you may or may not recognize this graph, but it's essentially Moore's law. So this is the thing that says how many transistors, so here we're at 1 billion, are packed into a single chip. And Gordon Moore essentially noticed this. I'll talk to you kind of about the history of this. But there's different types of Moore's law. So in memory, it's actually accelerating even faster, because it turns out it's a little, memory is just a bunch of the same thing over and over, where on the microprocessor you have different types of gates, so that they can be more aggressive in how they scale. And so the original Moore's law looked like this. So in 1965, when they had kind of, well, in 1960 there's one transistor, and then they got it up to 10 a few years later. He noticed that it was kind of scaling where it was doubling about every year or so. And then what happened was it kind of settled down to about 18 months to 2 years. Because this is a log scale, that the number of transistors on a kind of given area will double about every 2 years or so. And it's pretty much held to that. Now, how the transistors are used has changed dramatically. It used to be there was just, the microprocessors would come out and it was like 1 gigahertz and 2 gigahertz and 4 gigahertz, and everybody was like, when are we going to get to 10 gigahertz? Well, if you notice, nobody's at that today. Everybody's kind of around 1 to 2, depending on where you're at, maybe a 3. And what happened was they said, look, it's going to be much more power efficient if we break all these transistors into separate cores, so they're kind of mini CPUs. So in a classic sense, the number of transistors in a given CPU kind of stopped scaling, but the number on the actual chip kept going, and it continues to go. Okay, so why and how does it happen? So the why is really interesting, and the original Gordon Moore publication from 1965, he got it right away. It's all economics. It's not a technology thing at all. The only reason you're shrinking is because I get lower cost. So if you think about it, I'm processing one wafer. If I can get twice as many chips on it, or twice as many transistors in the same chip, that'll be faster. I can sell it for more money. Or like in the memory, I went from having 400 chips on the thing to having 800 chips at the same kind of density. So it's all, the why is Moore's law really there? It's an economic thing. Everybody kind of thinks technology, but there's a huge technology component, and that is how it happens. And what I did here is, on the y-axis is kind of the feature size of those transistors. So we're down, what did I have? I had 32 or 36 on some of those previous pictures that I showed you in terms of nanometers. Yeah, sorry for kind of mixing the microns and the nanometers. I'll do the conversion. And then again, kind of by time. So you've got this semi-log scale, same thing. And instead of number of transistors doubling, this is showing an individual transistor getting cut in half every 18 months. So I'm doubling, or I'm having the unit area, which effectively doubles the number of transistors I can put on a chip. And the point of this is, as each generation, you pick a year and say, okay, we were at 250 nanometers, 0.25 micron in 1995 in production. And in order to get down to 18 nanometers, we had to introduce copper for the wiring. Because up until then, it was all aluminum wiring. And the resistance of the aluminum got too high. We couldn't, when we shrink down to here, the aluminum just was too resistant. The chip wouldn't work. So you had to switch to copper. And all along here, there's just a tremendous amount of innovation that's continually happening. And it's not only in one place. So this lithography, remember we were talking about, we're imaging, that we're using light to kind of image the mask onto the wafer. Well, the wavelength that you use there determines the minimum feature size. And you can see they have to go to smaller and smaller wavelengths. And in fact, now they're working on extreme UV, which has a wavelength of 13 nanometers. And that allows kind of a classic shrink. I'm going to make every transistor smaller. But along the way, you can see there's so many other things that are happening. A lot of them materials related, so that's where chemists, chemical engineers come in. And then a lot of them are device related. So like this strain, they found out that if they put a layer on the transistor, and actually it puts some stress on the transistor itself and the silicon, it opens the atomic lattice just enough so the electrons can move through faster. I mean, it's such a subtle thing, but it's used in every chip now, with different materials as well. So here's nickel silicide, here's silicon germanium. Intel just came out with their new tri-gate. They're ahead of everybody, so they're taking, instead of a transistor that's kind of flat that I showed you there, they're moving it kind of on its side so they can get a much longer transistor length, but in the smaller size. Similar to the hard disk industry, where they used to have a magnetic particle sitting on the disk, and then they flopped it up on its side so they could pack them in more tightly. Same thing's happening here. And this 200 millimeter, 300 millimeter, we talked about the size of the wafer. So in the late 80s, early 90s, people went from 6-inch wafers to 8-inch, 200 millimeter wafers, because you get about double the area. Same thing in the early or late 90s, went from these 8-inch wafers to the 12-inch wafers, 300 millimeter. Again, a productivity, nothing to do with technology necessarily, but I get twice as many chips at the same size. And they're now, we're in the area somewhere out here, they're going to move to 450 millimeters, so 18-inch wafers. You can imagine doing, it's kind of an oxymoron, right? I'm taking something that is so small, nanometers across, and I got to do it across this giant wafer. There'll be trillions of them across a single wafer. But that's what the economics is forcing us to do. Okay. So I want to do another look at Moore's Law, because it really is what's driving the semiconductor. So here's the same thing, kind of same graph. So this is the technology note, the smallest feature, the critical dimension, we call it, the smallest thing, usually the transistor on the wafer. So if I'm sitting here, or in 2012, we're at about 38, 22, 28 nanometer features. So the transistors are kind of that size today in production. So you buy chips and fries, they have these things in them. And you can see where it's going. Okay, so that's great. If I'm memory, remember I said I'm a little more aggressive. I can actually shrink it faster because it's a little simpler to do. So now I am Intel over here, I'm Samsung making memory right here. Great. I need to, next year, have a 16 nanometer, a device that has 16 nanometer transistors on it. So when do you think they have to start working on it? They're not going to start next year. They've been working on it for a couple of years. So when they work on it, how do they test different options? Well, they have to have all the equipment that we just showed you. So that means Lam has to be way ahead of this roadmap. So I had to have something, if I take this, so the stuff that's being in the date, I had to have it ready for the customers 4 or 5 years ago. And then my R&D on this started back here. So it's interesting, if you're looking at semiconductors, you're like, oh, Intel's doing such cool stuff with these transistors. We're way ahead of them. The stuff my group's working on is down here, it's single-digit stuff. We're working on 7 nanometer, 8 nanometer stuff. This is really, that's why I use nanotechnology in the title. It really is. We're down to the part where we're kind of manipulating atoms to get this stuff to work. So that's why the equipment side, it's why I've stuck around so long, is it's really energizing because it's just constantly changing, literally bleeding edge technology, because the R&D we're doing, like I said, is way out here, and it'll show up at Intel 4 years from now. Okay, so what drives all this new technology? And it's kind of, there's NAND flash, this is the USB drive, the DRAM that goes in the phone, and then logic chips, and then there's kind of some other stuff hanging in the future. And there's just a whole list in every one of these areas where new technologies are needed. And I'm just going to kind of give you one example, and then we'll have time for some questions. Take the periodic table. You take a chip from the 1980s and you saw it in half, you start doing a material analysis, you would find these atomic, or these elements in a chip from the 80s. You go to the 90s and you have the green plus, they added a few more, right? So they added some tungsten, some tantalum as well. Now, if you go into 2000 kind of since, what's in the chip or what they're working at is just like everything. I mean, they're running out of, it's not just a shrink anymore. They gotta check every material. I mean, we've got stuff with the, I mean, literally. Not that every one of them is being used, but they're looking under every rock for a way to make these new chips. So you can imagine this is a great, hey, periodic table. This is what we do in chemistry and chemical engineering. Okay, I got a few slides up now, kind of Lam specific, our college programs. So Lam's been in business 30 years. We talked about we're worldwide. We get various awards every once in a while. The most recent one was we're a top 125 training guide. That's nationwide, right? Yes. Okay, that's good. 6,600 employees, 354 Cal grads in engineering business. And you can kind of see the mix here. So we're pretty heavy PhD in a relative sense. I mean, Intel may go a little beyond, actually probably as a percent, maybe not. And we have a number of scholarships and fellowships in a number of the departments here as well. Okay, we have a pretty aggressive intern program and what we call NCG's New College Graduate Program. Our intern program, I mean, this is a real thing. It's a pretty good, I wish they had that around when I was an intern. It's not just, I mean, we have jobs that the interns do, but they have a kind of coordinated program with all the, I mean, I give talks to the interns over summer. They went to Great America. I don't know how they do that. Yeah, okay. But it's, anyway, there's always free food, so it's a good thing. And then the other thing, when we hired the new college grads, we asked the managers how well prepared are they, and we're, right on. New college grad hires in the last year, 2011, 2012. You can see here 147. Again, fairly heavy in the advanced degrees. And then 18 of the interns ended up converting into NCGs. And then, well, we target mostly Bay Area, but you can see kind of nationwide. We have a facility in Walton, Oregon, so Oregon State's on there. We're going to, go to the top schools. Cal Poly is a great one for mechanical engineering. Yeah, you can see San Jose State, same thing. There's that other football school on there. Yeah, and then, for various reasons, there's actually a big program at RPI in Albany in focusing on semiconductors. So there's a lot of people coming out that are kind of trained in semi as well. And then we have a program where we have kind of alums from the different schools that kind of go back and help with the recruiting process. So we talked about kind of those core values. And so this is, you can see the core values are kind of embedded in here. But when we get a resume, I mentioned before, it's not just what's the GPA and what classes do they take, but it's kind of the whole person. And there's a lot of kind of the, not necessarily fuzzy skills, but we're looking for innovation. We want innovative people, achievement, obviously. Got to be a good communicator. There's just too many meetings to go to where it's a bad communicator will be beneficial. Okay. So some other specifics on it. We consider the end. You're not an NCG if it's more than 2 years. Sorry. And then obviously we look for the top people. And then here you can kind of see it's beyond just the engineering side of things in chemistry. I mean, you can imagine we're building these very complex machines. So our software is amazing on what it actually does, the precision that it has to work with, just like our physicists are amazing. But there's all kinds of other things. We got supply chain. I mean, how do you get this stuff built and delivered to Korea in time? And how do you make sure that we market it correctly, or we have the IT systems to kind of support our global infrastructure as well? Okay, internships. You can read it here, but it's actually as I said, a pretty good formal program. They're all over the map in terms of what you do. I mean, it just depends kind of what group and what they have for you. We actually have some scholarships that are based on core. I think we make them do an essay.
Yes. Have to write an essay, 800 words.
Yeah, so you got it. Kind of about the at the end of the intern thing, and so a couple people walk away with a decent check for the fall. We had 54 last year, and you can kind of see the criteria there. Okay, so here's the schedule, and Shirley can give you more details on this. We've done a lot already, I think, since this year. So we're here, MBA Career Fair. Yeah, there's more. But now's the time for, if you're interested, to get to know Shirley. And we're going to have other opportunities. There's actually, we've done a Lam Day at Cal in conjunction with a number of departments here, where we bring in people out of my group and they kind of give some research talks. We've also done the Cal Day at Lam, where they kind of come down and some of the grad students do poster sessions or give talks as well. Yeah, there's a bunch of other ways to kind of get involved. So, let me kind of summarize. Moore's Law is continuing to go. It's not going to end. I mean, you hear, read in USA Today, Moore's Law is ending. It's not. The reason it's not is there's still a bunch of innovation. And I tried to make the case that Lam and the equipment industry has to stay a couple of generations ahead of this very aggressive roadmap. Every generation seems to get harder, yet somehow we always kind of pull through. And you can see that we're broadening kind of the tools that we're using to solve these problems. And as I mentioned, we need a lot. It's a team effort. I mean, it's fun working with. I mean, I ran the robotics group and the software group in addition to kind of the process R&D group as well, and it was great. We also have kind of business people and marketing people as well. But the bottom line is it's a great place to work, and I think our employee surveys and the retention that we have really bears it out. So I'll take questions and answers, and when we get close, I'll give you a couple of interns, Dilberts that you can look at. So otherwise, I'll take questions. You don't want to be an intern to an intern. That's the bottom line. Yeah, go ahead.
So are you guys working on your lithography stage?
So yeah, so the way we hold the wafer, very important. So since we're not doing the lithography part, our wafer holders are a little different, because in those cases you have to have alignment, right? I got to get the mask aligned exactly with the pattern on the wafer. Our stuff is more focused on, we're in a vacuum a lot of times, and so I need to control the temperature of the wafer, but I can't pull a vacuum on it because I'm already in a vacuum. So we actually have an electrostatic clamping mechanism that sucks it down like an old, HP plotters used to do that with paper. They form an electrostatic charge on that, and it sucks the back of the wafer down electrostatically. And getting that engineered correctly so it sticks, releases, and it's in this plasma situation. We got lots of groups working on wafer holding and temperature control of that as well. And you can imagine also in that wet cleaner, how do I get this thing to spin and do it reliably and in a way that I can heat and cool the wafer at the same time?
Yeah, I had three specific questions. The first one was, when you guys were doing the etching, you have the photoresistor on top, but you also have the material right underneath it. And when you're going through the etch process, there seems to be a surface on the side which is exposed to your plasma. How do you protect that, like the plasma coming in from the side?
Yep. Let's go back. So, yeah, while you're etching right here, right?
Yeah.
So, there's kind of two high-level ways to kind of explain that. One is, if I make this it's an ionized plasma. So I've got a bunch of positively charged atoms, essentially, or elements. So I'll get like a F plus. And by putting power on here, I can cause a sheath. I make the wafer kind of appear negative, is a simple way to do it. So there's an electric potential, almost a DC potential, between something up here and the surface of the wafer. So what that does is it accelerates them in a vertical fashion. So one answer is all the ions are actually directional. They're coming straight down. now. I wish life were that simple. Because what happens is there will be some neutrals. It's not fully ionized, and stuff can surface. It'll hit the surface, maybe it doesn't react, and it can migrate. It can diffuse along the surface and then start to react. So it's a good question because you can end up with, undercut where the etch kind of comes in there. And so what happens is you will tailor some of these byproducts to actually stick to the walls. So that stuff I need to clean off, I may have put it down on purpose because it's almost like a little piece of Teflon or something that as I'm etching it down, it'll be building up a small, thin protective layer that I then have to remove with that either strip step or the wet clean step.
On the PVD stuff,
Yeah.
how did you guys? I mean, how consistent is the film?
So it's as consistent as your plasma you can make it. So there's a ton of tuning. In fact, to be honest, what happens? I mean, it's one of the most complicated systems we have. Plasmas, charged particles are repelled by magnetic fields. So we actually embed magnets in the walls of the chamber to keep everything focused, so it doesn't, because otherwise the plasma will just kind of go everywhere. So we'll have it where it's a magnetic bobble essentially that reflects the charged particles back, and then you do that to make it uniform. But again, it's a lot, one of the tough problems we've got. Yes?
When you were talking about how you're using much more of the periodic table processes now, if you're working on such small scales, how does using these large
Yeah. Well, fortunately, most of the stuff we're looking at is still above atomic. I mean, even the atoms, the big ones, are small enough. But you're right. A lot of the materials that are in that category are going to be deposited. So we're going to make a monolayer of one of these, like the hafnium stuff we were talking about, the hafnium oxide. And you're not going to be using them for the etching or depositing in a very small feature. You're going to put it down and kind of remove it step by step. So
so this is also kind of about scale, but do you think we're going to see like a minimum technology node distance in our lifetime?
yeah, I mean,
If you're getting down to like the angstrom length.
no, I know it should, right? Everybody, and the point of this is it hasn't happened yet. And kind of as far as we can see, I remember back in the late 80s, early 90s when I just kind of get started in this, there was a big warning that it's going to end because you can't print stuff smaller than the wavelength of light. And it's like you're dead because it's like the 257 or 248 nanometer. So that's huge compared to these transistors. So